It is all about exponential functions. And here's the big part that you've got to realize when they're talking about exponential functions. Is before, when we were doing the quadratics and all the polynomial functions, we had x squared or x to the third, that x was in your base. Exponential functions, it's going to flip it around. And now you're looking at 2 to the x power. So before, where we had y was equal to x squared, now we're looking at y equals 2 to the x, where, and they say for just a basic problem when we look at this thing, they say it's y equals b to the x power. That your b is your base. And the big thing is that x is now in the exponent, and that's what makes it an exponential function when we start going through this thing. They start off with a couple of small, I guess, basic things on this part that they look at. They say, all right, just to get us started, and then we'll change a little bit as we go along. But to start off with, your base has to be bigger than 1. Sorry, it has to be bigger than 0. But your base cannot be 1. Because if you let your base be 1, it's a trick question. Because 1 to any power, when you come back to it, is always going to be 1. Doesn't matter what it is. 1 to 1 times 1 times 1 times 1. It's just always 1. So you cannot use 1 because it's a trick question. You kind of go that route with it. Okay, so when they're talking about exponential functions, that's kind of what they're looking at. Here's the big thing that we're looking at when we're going through these. You've got to remember a few basic principles on this thing when it comes down to it. Let me kind of backtrack as we're going through this one. The big thing we've got to worry about, or kind of think about, is let's say that you're doing 2 to the 0 power. And before we get the answer on that, we'll kind of back up for a second. Let's start with something like this where we're doing 2 to the 3rd power. That if you do 2 to the 3rd power, that's 2 times 2 times 2. Multiply together, that would be 8. If you had 2 squared, 2 times 2, which would be 4. If you had 2 to the 1st power, that would just be a 2. Not do anything to it, so that's just a plain old 2. Here's what you got to realize. And this is where a lot of times people get thrown off. And I remember when I went through this, I always got this one a little bit backwards. And had a teacher show me this one time. And then once they showed me this, it made perfect sense. They said, all right, if you're counting down till you get to 2 to the 0 power, what happens every time when you take away a power? How do you go from 8 to 4? Well, you're getting rid of a 2, right? You're basically dividing it by 2. That if you knock a power off, you're dividing. If you go up a power, you multiply by 2. If you come down, you're dividing it by 2. Take a power off here. 2 divided by 2 is 2. If you divide by 2 again, 2 divided by 2 is 1. So, and that's going to be the case for anything. So anything, any base that you have to the 0 power is always going to be 1. And I always used to think it should have been 0. And then finally somebody said, well, let's just pretend for a minute that let's say 4 to the 0 power is 0. Well, if you go to 4 to the 1st power, you've got to multiply by 4, right? But what's 0 times 4? 0. If you want to go to 4 squared, you're still going to multiply by 4. But again, it was 0, so that would also make that 0. So if you don't let it be something other than 0, then every answer you do for every exponent is going to be 0. So that's why, if you kind of think about it that route, that's why something to the 0 power has to be 1. If you think about exponential functions, you can't make something out of nothing. If you want something to grow exponentially, you've got to have something there to start with. You know, if you want to retire, you got to put at least $1 in to start, right? If you're Louis Pasteur and you're trying to grow bacteria, you got to have a little bit of bacteria there, right? You can't have a perfectly sterile environment, because if it is, there's no growth, there's no bacteria, you don't have anything to start with. So you've got to have something there to start with it before you can kind of move on and go from that route. Okay, so that's the biggest thing that you want to kind of look at. Now, you can do things around this. You know, whether you do 4 to the 0 power, that would be 1. Now, here's where you got to be a little bit careful. You do negative 6 to the 0 power, that would also be 1. Now, you could add, subtract, multiply some things around it and get something other than 1, because you could have 3 times 2 to the 0 power, which would be 3 times, do your exponents here first, that would be 1. So you could do 3 times 1 and make it 3. But, generally speaking, if you do something to the 0 power, it's going to be 1. Now, you can add things around it to change it, but anything to the 0 power would be 1. Where you have to be a little bit careful is if you have negative 6 to the 0 power and you don't have parentheses, then technically this would be negative 1 times 6 to the 0 power. And again, if you do 6 to the 0 power, that would be 1. So really it's negative 1 times 1, so that would be negative 1. Well, and it comes down to parentheses in that case. That if you have the parentheses rounded, it's the entire thing to the 0 power. This is the negative of 6 to the 0 power. So you have to do the 6 to the 0 power first, and then you go back and put the negative back out front. So you almost have to kind of think about it that way. So the parentheses in that case makes all the difference. If it's no parentheses, it's just understood the whole entire. Yeah, just separate the negative out front. Yeah. Depends on how they put it. Like for this one, like if you do negative 6, the whole thing to the 0 power, that's going to be 1. Because some of the problems in the homework, they'll have them set up this way, that they'll give you this problem, and then they'll turn right back around and give you this problem. That if you have a negative 6 to the 0 power and you don't have a parentheses around it, then it's basically, the answer will always be negative. You'll still do 6 to the 0 power and make it 1, but the negative is separate from the exponent part. That it's really like negative 1 times 6 to the 0 power. If it was 6 squared, if you go back to that part, if it was 6 squared, if it was negative 6 squared and the parentheses is here, it'd be negative 6 times negative 6, which would be 36. If it's negative 6 squared, it's the negative of 6 times 6, so that's the negative of 36. So that'd be a perfect example of the way of thinking about it. The parentheses with negatives, and that's where it's the negatives really that get you there. You've got to be careful with the negatives because that depends on how many times you're going to use it, depending on the problem and how it's set up. But we'll come back and keep working on that. And that's some of the problems that you'll kind of run through when we do some of these parts. That not always, but sometimes the negative makes a big impact on how you run through those problems. Okay, so here's one. If you've got your scientific calculators, go ahead and take those out. We'll do a couple of problems. If you don't have one, if you want to be able just to kind of get through the homework, you can always use your cell phone just for problems working on the test. Working on problems in class or on the homework. Just to get you, and we'll come back to the parts of it here in a minute, but just to make sure you can kind of work through some numbers on here. Let's say you do 4 to the negative 2 power. Should get you 0.0625. Everybody get that? Let's see here. Alright, should find an E button on your calculator. Let's do E to the 2.3. Should be, in this one you have to round off to 3 or 4 decimal places, 9.974 if you round it off. Alright, let's do one more here. Let's do 3 to the square root of 5. Power. Okay, should get you 11 point, and again, another one you have to round off, 11.665. Okay, so that's just a few problems, and again, just get used to using your calculator because we're going to keep coming back to it and doing some different parts with it. Here's where we're going to come back to the exponential part, back to this equation, the y equals b to the x power. The big thing they're going to have you do in section 1 is they're going to get you used to just working with the exponential function a little bit. So the very first thing they're going to have you do is get ready to graph some of these. And basically right now we're looking at two main types of graphs. So very first one we'll look at is y equals b to the x, where your base is greater than 1. And what we'll do is we'll kind of go back, instead of recreating all these, we'll go back for just a second here. But flashing back up for just a minute to when we did the 2 to the power. We'll kind of go back and use this for a chart. That basically this was our equation we had here. Same equation. If we had 2 to the 0, it was 1. 2 to the first, it was 2. 2 to the second, it was 4. 2 to the third, that was 8. So if we were to graph this one, we would have had, we took x equals 0. If we go back and do the chart here, we had 2 to the 0 power, which was 1. 2 to the first, which was 2. 2 to the second was 4. And 2 to the third was 8. That the exponent was basically the x part of the coordinate for this thing. So if you look at ordered pairs on this one, this is our x, and this would be our y. So this was at 0, 1. This would be at 1, 2. This would be at 2, 4. And this point would be at 3, 8. So again, there's that dot. There's that something of we've got to have. That's something that we've got to work with. If it's bacteria, or if it's money for investing, you've got to have one something, at least one penny to start with to do some investing with. Then you've got 1, 2, which would be here. 2, 4 would be here, and 3, 8 would be, somewhere up here along the line. And then you come back and connect those dots together. And with the exponential graphs, what they do is they say, well, all right, that's if our base is greater than 1, we'll do this. We're still going to, let's say that you've got, instead of $1, you could still have a fraction of a dollar. You could start with a quarter or 50 cents or 75 cents or something. So they even look at it that, the exponent, the base that's here could be less than 1. As you're working through this one, or the value we're going to plug in for x here, it could actually go back a little bit. So here's where they're going to go back and add in a couple of things, and this is where we'll add to it here. What about 2 to the negative 1? That when we walked through the earlier parts, we looked for everything where the base was positive. Again, we started at 0 and greater. We kind of looked at what was happening there. We didn't walk it back down. The last thing we said we had, 2 to the 0. If we walk back through this one, so in the other order here, if we had 2 to the negative 1, this one we were dividing it by 2, dividing it by 2, dividing by 2. If we had done 2 to the negative 1, we would take this answer and divide it by 2. So 2 to the negative 1 would be 1/2. So if we had x for negative 1, that would be 1/2, which would be somewhere about there. If we had 2 to the negative 2, we would still take that same answer and divide it by 2. And you could rewrite that one as 1/2 divided by 2. And again, if you go back to your 7th or 8th grade math, that's where you're going to keep it, change it, and flip it. So that is 1/2 times 1/2. Make that a fraction there at the end, make that 2 over 1. So that would make that 1/4. So that gets even smaller. Now, and here's the big connection they're trying to make you to see when you're going through these numbers. If you're good with all the positive exponents and how those work, The only thing you have to do different with a negative exponent is take the answer you would have here if this exponent was positive. If we just pretend for a minute this was 2 to the second. It's the same answer as here. You just have to put it as 1 over that one. So if we want to do 2 to the negative 3, that's just going to be 1 over the answer of 2 to the third, which would be 1 over 8. So that's all you've got to see when you're going through the negative exponents. It's the same answer as the positive exponents, but anytime you do a negative exponent, it's basically just the inverse of whatever the whole number would be. And that's kind of the big thing that they get you to look at is that, all right, if you've got, 2 to the negative whatever, that's the same thing as 1 over 2 to the third. And then you can work out the 2 to the third and get whatever number you need there. So that's kind of the thought process as you're working through those to get those numbers. Okay, so we finished this graph out. This thing is going to bottom out, but again, it's going to get really close to 0, but never quite get to 0 because, again, you've got to have something there to start with to get this exponential function going. So it's going back to what we were talking about in chapter 2, you're going to have an asymptote sitting right there at 0. You can get as close to it as you want to, you'll just never touch the 0 value because you still have to have something there to make this exponential function grow. Alright, and that's for any exponential. As long as the base is bigger than 1, they're all going to have this same shape. The only thing that would change is if you change this base to 3, and we're not going to graph it here. The only thing that's going to happen is that it's almost like that's the slope. That this slope, if the base was 3, would be just a little bit steeper. Now, it's still going to cross at 0, 1. Still going to cross at this point. That's going to be the same no matter what we do. If your base was 4, it would be just a little bit steeper on this end. But again, it's still going to come back and cross over here. If the base was 5, it would be a little bit steeper. If the base was 6, it would still be a little bit steeper because that growth is going to happen that much faster. If you put $1 into your account and watch it grow exponentially, it's not going to grow as fast as if you put $6 in. So that curve is going to be, that graph is going to go up a little steeper because you're putting more into it. It's that same thing here, that it's going to be, the more you put into it, the steeper that thing is going to go as it kind of climbs up the graph. Now, you're not going to have to graph 1 or 2 or 3 different things. You're just doing one graph, so as long as you get the basics of it there, it should be fine. Okay, so if your base is bigger than 1, if your base here is bigger than 1, it's going to have that basic shape, and that's basically a growth, because that's your exponential growth if you want to look at it that way. The other one they're going to have you do is exponential decay. Where your base is, again, somewhere, we're not going to use 0, but it's somewhere between 0 and 1. And again, we're not going to use 1 because that's a trick question. We're not going to use 0 because that's kind of also a trick question. So, again, you got to have something there to start with it and get it to grow from there. But basically, this is your decay. This is your carbon-14 dating. We take something out of the ground, check how much carbon's in it, we should have an idea of how old this thing is. Hopefully it's accurate, but we don't really know. Because if something's 50 million years old, we don't know because nobody was there to see it. It's just a guess, right? It's really just a guess. We don't know. Nobody can scientifically say 100% that that's exactly how old it is because nobody's there to write down the history, so we don't know. Now, this part of it is going to be the same. The one thing that's the same is, again, no matter what you do, the base to the 0 power, regardless of what it is, whether this is a half or a third, or 0.1 or whatever the base is, doesn't matter. Anything to the 0 power is still going to be at 0, 1. So that part's still going to be the same thing. The difference in the graph this time is that instead of the graph getting bigger as you move to the right, if it's decay, it's going to get smaller. And everything beyond back here would basically it's just a growth model, just turned sideways. That now the growth of it would be back here. If we could go back in time, and go through it, basically you would have this growth that was coming back here. That, if there was a million dinosaurs and they started to fall off and we finally got one, and then, whatever went from there. It's basically just a reverse model of the growth function. Everything still works the same thing. You still have the asymptote that would be here. That again, it doesn't matter how long you go with this thing, there should always be some trace amounts of, if it's carbon-14 that you're dating, there's always some trace amount of carbon-14 that's there that you've got to get. Past that, that's your that's the big things you're doing with the graphs right now. So you're basically looking at a growth or decay model. And what they have you do is they say, all right, well, we're going to go back to everything we did back in Chapter 1 and Chapter 2. What happens if you've got a growth model? Let's say you're going to have to graph y equals 3 to the x power. Well, we know the graph would look something like this. The one thing that we know without having to do a whole lot of work is that this point is going to be at 0, 1. That's for this chapter, that's our new reference point. 0, 1 for exponential functions, that's your reference point. Just like before, everything else we're doing in Chapter 1, Chapter 2, it was 0, 0. But because it's exponential growth, you have to have something. So 0, 1 is our new reference point when we're looking at everything exponential function-wise. And what they do is they say, all right, well, let's just do something simple with this thing. Let's say that instead of giving you this graph, let's ask you to graph y is equal to 3 to the x plus 1. And this is going to go back to everything we were doing back in Chapter 1 and Chapter 2. Where that part that you add to it makes all the difference in which way you go. Anything that's inside, so if you add or subtract, here's the keyword again. If it's inside before we said it was the square roots, if it was inside the square root, if it was inside the brackets, if it was inside the parentheses, that it always took it in the opposite horizontal direction. The only thing we're changing for Chapter 3 is that now instead of it being inside all those things it was before, now it's inside the exponent. So it's opposite horizontal movement. Yep. So that's the one thing they're carrying over, is that where it is makes all the difference. If it's on the inside, it's still going to be opposite horizontal. If it's on the outside, or in this case, if it's not in the exponent, then it's going to be the vertical direction in the normal way you would go. So if we were doing 3 to the x plus 1 normally we think to the right side, but because we're going to go opposite direction, we're going to the left, so basically that would put this point back here, or that would be at negative 1, 1. Now, one thing they might ask you to do past that is, just so that you've got some kind of marker, they may ask you to find the y-intercept. Which really just means you're going to plug in 0 for x. So for this one, that would be y is equal to 3 to the 0 plus 1. Well, that's just y is equal to 3 to the first, so your y value would be 3. So that would be the point at 0, 3. So at least that way you know where this graph is going to cross the x-axis, the y-axis, that it should be up here at the value of 3. So all we've done is we've taken this graph and we've scooted everything one space to the left. If we'd marked it back here, this point would have been at 1, 3. Well, again, now we're just moving it back one spot, so now it's at 0, 3. If we did 2, 9, we'd back it up and make it 1, 9, because we're just moving everything one space to the left. So that's, and again, they're just going to get you to come back and think about it, that now all we're doing is that we're still taking that same graph, but we're still going to shift it in the same direction depending on whether it's in the exponent or whether it's outside the exponent. And they shouldn't trick you. If something's on the outside, if it was y to 3dx, it should be really like that one. It should be really obvious. Test-wise, I won't make it where it's kind of in between. And if you get a problem and you're not sure, you can just ask me, hey, is that inside the exponent or is that outside the exponent? I'll tell you, because I'm not trying to trick you. I want you to know exactly where it's going to be. If we're doing 3dx plus 2, sure. Mm-hmm. Mm-hmm. All right, so if we do y to the 3x plus 2, in this case, the plus 2 is on the outside. So if you add or subtract on the outside, then the result is a vertical shift. And that one is in what we call the normal direction, because you're going to take whatever the answer is, and after you have your answer, then you're going to add 2 or subtract 5 or whatever. So plus will move it up, minus will move it down. Okay, so for that graph, and here's the way we'll do this one, just so we can differentiate what we're doing. So in my mind, what I'm thinking is if I'm looking at just y equals 3 to the x power, that graph would basically be this. Now we're not going to. That's just a visual to kind of make sure that we understand what's going on. So that point would be at 0, 1. Y to the 3x plus 2. That's the actual graph we're going to do. All we're going to do is we're going to take this graph we have, and because of the plus 2, we're going to scoot everything up 2 spaces. So this graph would actually be. The blue line would actually be the actual graph. The y equals 3 to the x power, which is kind of what you think it would be the dashed purple line there. And the one thing that they may or may not have you do is that would be an asymptote that would be there. That again, you're going to, instead of bottoming out at 0, now because we screwed the whole graph up 2 spaces, now we're going to bottom out at 2. So you can almost take that line back out and just have it so it's that blue line. And again, this point would be at 0, 3. So we're just kind of using the y equals 3x as like a baseline to get the image of it, and then we can move it up and down and left and right to get the graph that we need there. The last formula they give to you, as far as dealing with exponential functions, and this is where it comes down to the money part of it, is there's 2 different formulas they're going to give to you. You have exponential growth or continuous compounding. And that's your formula. It's P times e to the RT power. Now, they give you we talk a little bit about e now, but we'll really come back in section 2 and 3 and dig into it a lot more. They just kind of throw it out there at you. Yes, e to the exponent RT. The other formula we're going to use is basically it's the non-continuous. This would basically be your monthly payments. It's 1 plus r to the nt power. Sorry, not 1 plus r. That's a different formula. Hang on, get the right formula here. 1 r divided by n to the nt power. In both formulas, the P is still the principal, which is your starting amount of money. R is your rate, and the biggest thing with the rate is that has to be as a decimal. That most of the time they're going to give you that as a percentage. If that's 5%, you've got to know that that's going to actually be 0.05 if you convert it as a decimal. You just got to move it 2 places to the left. T is your time in years. And that's everything you need here, because E is just the button that you're going to use on your calculator, so there's nothing there. For this formula, though, the N, that's the number of compoundings that you're going to do. And they shouldn't get too crazy when they talk about what the N value is. It should be monthly. Monthly, there we go. Where, it'd be 12, daily would be 365. Could be quarterly where it's 4. It might be, they shouldn't do anything where it's like, they might do something where you give you biannual or bi-yearly or something. But hopefully they'll just be monthly or daily or weekly or whatever they're going to do. And occasionally, sometimes they may give you daily and they may say use 360 for daily. I don't know why, but sometimes they'll just do that. Again, it could be quarterly. See if I can spell it right. Yeah, theirs is almost continuous. They should just give you one problem, and they're going to kind of tie this thing together. They're going to give you one problem here, and with the one problem, they're going to ask you. It's basically going to be a comparison problem. They're going to say something like this. Suppose that you have $12,000 to invest. And then they ask you, okay, which one of these is better? Because again, you go to the bank, they'll give you options on how you want to do this thing and set it up and all these different rates that you get. So let's say we're going to do this for 3 years, and you got to figure out which one you want to do. Which one's better? Do you want 7% compounded monthly? Or 6.85% compounded continuously. So they're going to make you kind of figure out which one it is. And again, it's basically two problems in one. They just get to the end and say, all right, which one's better? And sometimes they may, I think in some online homework, they may say, okay, give me the two amounts, and you may have to put the two amounts in there, and then you say, all right, which one was better? Something along that line. They're going to make you do both of the problems here to kind of make sure you know what you're doing. Okay, so we know our principal is $12,000. We know our time is 3. And then we've got two options. We're either going to do the rate is 0.07 and the N is 12, or with a principal of 12,000, our time of 3, if we do the continuous, our rate is 0.0685. And all we're going to do is we're going to do those two examples, and we're just going to see which one comes out to be better. Because there's our and again, continuous means we're going to have to use PE to RT. Okay, so for this one, we're just going to go back and work the two out and see what it's going to be. And they should be both really close because of how they set this thing up. And it's, I guess, no different than if you go to the car dealership and you're going to buy a car and they say, well, you can get 0% interest free financing for 5 years, or we can give you 4.5% and give you $2,000 cash back. And you have to figure out which one you want to do. You run the numbers and see which one it is. It's that same kind of thing of, all right, here's your two options, which one sounds good to you? Alright, so the amount we're going to get is going to be 12,000 times 1 plus. The rate is 0.07 divided by 12. And then it's going to be 3 times 12 for the power. Okay, I'm just writing this one down. We're going to work the problem out here. I'm just writing this one down so we won't have to keep scrolling up and down so much. Okay, so we're working the problem on the left. Sticking with it first. And here's one where, again, depending on the calculators and how you want to go through these. I'm going to go ahead and do the 0.07 divided by 12. And get that number, which is 0.00053, and add 1 to it so that I can do this all in one step. So this would be 1.00583 repeating. Now, and on these problems, don't round any number. If you get this long runoff number like this one's going to be, when you do 0.07 divided by 12 and you get the 00583, don't cut anything off. Leave as long as you can in your calculator. When you get to the very final answer, that's when you cut it off. So this one would be 12,000 out front. The one other thing you could do is go ahead and do 3 times 12 and make that 36. So now you're going to take this 1.00583 and do that to the 36 power. Okay, so for that one I had 1.2329255 and whatever else that would be at the end of it there. And we're going to multiply that by 12,000. So you get $14,795. And this is where you would actually round off. That should go to 11 cents. Because if you round this off back here before you get here, it's going to throw this number off. Now, it may not be by much. It may just be by a penny. Sometimes maybe 2 pennies. But talk to the accountant wherever you work and ask them what happens when they're off by a penny. They spend hours going back and finding out where that 1 penny was off. Because they have to. Okay, for this one, for the PERT formula, we're going to do, and again, depending on the calculators, for this one, I'm going to go ahead and do the 0.0685 times 3. So that's e to the 0.2055. So that's 12,000 times that. If you do e to this power, that should be 1.2281389. Everything else after that. Again, that's times 12,000. And here's one of those problems that when you get here, you can compare the two. This one is 1.23. This one's 1.22. So we already know that this one is going to give us a little bit more money. We just don't know exactly how much until we multiply it out. So this one is $14,737.67. So not by much. $58 looks like.